In the last video, we talked about fungible tokens and the ERC20 token standard. And that's useful when you have a token contract that creates a large number of identical tokens. And so essentially you just have to track the balances of each individual owner, but it doesn't really matter which of these tokens they control. But that's completely different with non-fungible tokens, or NFTs for short. Each of these tokens has its specific attributes and characteristics, and it makes a difference which of them you control. So you have to track them individually as individual objects, essentially. And the standard for creating these non-fungible tokens is the ERC721 token standard. That's exactly what we're going to look at right now. All right, let's go. Last time we talked about fungible tokens, and I think the best to revisit that concept really quickly is to make an example. And one example are stablecoins. If you have an issuer who creates a stablecoin, let's say a US dollar denominated and off-chain collateralized stablecoin, then it doesn't really matter which one of these stablecoins you hold. The smart contract essentially just stores a balance for you for your address. And each and every one of these tokens by the same issuer are the same, with the same risk. So you don't really care which one, and neither does the smart contract. In fact, the smart contract does not differentiate between these tokens. It's really just a value, a balance, as you've seen last time. But when something is non-fungible, when there are multiple different objects which have to be tracked on the smart contract as tokens, then it's different. Then of course they all have their unique characteristics, attributes, and then you start caring which one of these tokens you control. So think of a smart contract that, for example, traces ownership of art. You have different paintings. Since it's not the case that one painting is the same as the other, they are all unique, you have to track them and trace them individually. So they will, as you will see later on, get their identifiers, and it will be important which one of these tokens you control. And that's exactly the concept of a non-fungible token or an NFT. Now, there are lots of examples when this can be useful. I already mentioned art, but you will see that there are also, for example, collectibles. You can think of trading cards on the blockchain, like football cards or sports cards more generally. You can think of domain names. So there's this concept of Web3 domains that can be used either to abstract a wallet address or to point to a website hosted on IPFS as an example. Then in many cases, metaverse parcels are represented as NFTs. So the land ownership in the metaverse is in itself an NFT, and you can transfer that ownership by transferring the NFT. But it can also be in a more traditional sense a financial asset. So when these financial assets have unique characteristics, then of course you will not use a fungible token, you will not use the ERC20 token standard. Then you need some way to capture these unique properties, and that's also done through an NFT. I think one of the most prominent examples are in-game assets. The idea that in a computer game, when you're getting an item, that this can also be represented in a way that, at least in theory, will be transferable to other computer games or other ecosystems, and then it's also represented as an NFT. And last but not least, tickets or special privileges for events. Even in some cases, things that could be considered part of your identity can be represented as an NFT. So there are countless examples, and it's extremely important to understand not just ERC20 and the fungible tokens, but also 721, which is the dominant standard for non-fungible tokens. As of ERC20, any external promises, and that's extremely important to be aware of, are subject to counterparty risk. So it's quite straightforward. The token standard and technical implementation doesn't change anything about the fact that whenever you have an external promise, whenever somebody is promising you to deliver something in the real world for the redemption of that token, then it's subject to that person's willingness and ability to actually deliver their promise. So that's exactly the same as with any token for that matter. Now, if you have to differentiate ERC20 and 721, I think it's best if I show you in these tables. It's super simple, as you have seen with ERC20 ERC720, you simply have the addresses and then an amount. So these are basically the balances. And as I've mentioned, since it doesn't really matter which one of these tokens you control in the contract, since they're all the same, it's perfectly fine if you track the amount, so the balance for each address. So the mapping is from the owner to balance, with the address of the owner being the key of the mapping. So that's basically what you're asking for. And with 721, it's a little different. With 721, you have the token ID. So each and every one of these tokens has its unique ID. And then you assign an owner to that ID. So it's not that there is an amount or a value. You can, of course, ask for that, as you will see later on. But the way it's stored is that each and every one of these token IDs gets assigned an owner, which essentially is just the address. So it's also, in terms of how it is stored, it's a completely different concept since it has its unique properties. Now, you are to some extent already aware of that, but it's good to quickly revisit it. Token standards, the idea behind it is it's like an interface, you can think of it a little bit. It allows third-party contracts to use the tokens in a standardized way, which is important. Otherwise, if you implement it without a standard, any third-party protocol or even centralized exchanges for that matter would have to treat each and every one of these token implementations separately and individually, and that would not be very efficient. You have to be aware that it's a minimum requirement. We'll also talk about some extensions in this slide deck. You will see what I mean by that later on, but it's really the minimum standards that have to be implemented in order to be, in this case, ERC721 compliant. And some functions you will already be familiar with just from the last video, from the ERC20 video. For example, when you look at the balance of, it's pretty much the same. I mean, might be not the most intuitive with non-fungible tokens, but what you're doing with balance of as a function argument, you're giving the address, so the owner address, and you're getting back how many NFTs this address owns. The function does not return anything that would allow you to identify which of these tokens the address controls, but it's just a general indication of how many of these tokens are owned by a specific address. And then you also know transfer from, you know approve. It's the exact same thing, or pretty close to what you got to know in the ERC20 token standard. But much more exciting are the things that are new, so some additional functions. And the first one is the owner of. And owner of, the idea is you get the owner of a specific token ID. So owner of, the function argument is the token ID, unsigned integer, and it simply returns an address which happens to be the owner of that specific token. The second one is set approval for all. This is used to set or revoke the approval for all the tokens, all of your tokens in that specific collection. And this is an important concept when we talk about a collection. Again, I'm not a big fan of that word. It's not too intuitive, but it's standard, and it means all of the tokens of a given NFT contract. So when there is an NFT contract, for example, with, let's say, some artworks, some paintings, digital paintings, then all of these paintings would be referred to as the collection. Okay, so it's the entirety of the NFTs represented by that smart contract. And basically set the approval for all of them. So you can give where are we, right here, set an address and say, I approve this address to spend all of my NFTs which are part of this specific smart contract, so of this specific collection. And get approved is basically requesting the address that is approved for a specific token. So you're saying, okay, I have the token with the token ID, let's say 1, and then I get back the address for the account that is approved for the specific token that happens to have token ID 1. Of course, there are also events. I don't think I have to tell you too much about these events because the concept is exactly the same as with the ERC20 token standard. When there is a transfer, then you will see a transfer event. When there is an approval, then there will be an approval event emitted. And of course, there's the approval for all, which essentially is just when somebody approves the entire collection or all the tokens they own from a collection to a specific address. Then there is a further addition, and that's called safe transfer from. And it essentially treats the problem that sending tokens to a smart contract which does not know how to handle ERC721 tokens would result in a loss of the assets. So in other words, when you're sending your NFT to a contract account that doesn't know what to do with it, that doesn't have a function to handle it, functionality, then it would be lost, and that would be really bad. So when you're using the function safe transfer from, the token contract checks if the receiving contract knows how to handle these ERC721 tokens, and it effectively only sends it when that's the case. So in the first step, it looks, is it an EOA? When it's an externally owned account, then everything is fine. With an externally owned account, of course, you have the flexibility. So the recipient will always be able to transfer these NFTs later on. But when the destination address, so the recipient is a contract account, then there is a check in the background, and we'll come back to that on the next slide. If the contract account is designed in a way that it can handle these ERC721 tokens. Now there are two different functions, as you can see right here. They have the same name, but recall that they still have a distinct function selector because the arguments are different. And here you have an additional one, which is a bytes argument with the name data. Basically, you're simply sending some data along, which can be used to decide whether or not to accept this transfer. In most cases, people will use this function right here without the data. In the background, it will still forward the call to this function, but of course with an empty data field. So simply because it's not needed. There are very, very few cases. It's quite rare that NFTs use this option right here, but it's still important that you have the flexibility. That's why it's implemented. Now, this concept is, of course, related to ERC165, where you basically can check if an interface is supported by a smart contract. We already have talked about that in the inheritance, interface, and library slide deck. And basically what you do also in the case of 721 is exactly what I told you in that earlier video. You take all of the function selectors from which are expected to be part of that interface. In this case, it's all of these functions from 721, and then you're just XORing them together to compute the interface ID, and then you can check for that interface ID. And it's basically the idea to check if the interface is implemented and published on that contract. And if that's the case, you can interact with it. Otherwise, it might not be a contract that adheres to these standards. Now, why is this useful? Imagine, I told you we will talk about extensions. So there is the enumerable extension, for example, later on. And if you want to know if it's standard ERC, plain vanilla ERC 721, or if it's ERC 721 with the enumerable extension, then that's exactly the way to proceed. And you have a very efficient way to basically ask the contract which of these interfaces are implemented on the contract itself. And again, as always, there would be various ways how you could do that, but it's always a good idea when there is a standardized way how to do it, how to request this information. That's exactly what ERC 165 is about. So as you can see, you have the function selectors right here. As I mentioned, you XOR them. You can think of it a little bit as it's obviously it's not a hash function. It's XORing. It's something distinct. But from the intuition-wise, it's pretty much the same. What you're trying to do is you come up with some representation for the interface which combines all of the information from the individual function selectors which are part of that interface without making the information any longer, and make sure that when there is some variation in there, that there will be also variation in the interface ID. So it's even though it's not a hash function, it's quite similarly on an intuitive level what it does. And at the end, you just have this one representation that you can check, basically ask the contract if that interface is implemented. Now, with that, we are already at the first extension, and I have to give you a quick heads up on that. It's somewhat confusing. In the specification, it's called the enumeration extension. In practice, on OpenZeppelin, whenever it's implemented, it's usually referred to as the enumerable extension. So that's what we also decided to go for. The idea is that there should be a way to circumvent the problem, that the mapping only works from the token ID to the address. It's important to understand that if you wouldn't have this extension implemented, and there would be no way to get all the tokens of a specific address. Okay, so you basically couldn't ask. You can of course get the total, you can of course get the balance of a person, so of an address, but that's just a number. But as I said earlier, you wouldn't get the actual token IDs which are controlled by a specific address. And the goal of this extension is to provide you with an option to simply ask for an address and get the token IDs that you can see, not just how many, but which of these tokens are owned by a given address. The way it's implemented is you have this index by owner right here, and then the first one simply has the index 0, the second one which is owned by the same address has index 1, third one which is owned by the same address has index 2, and so on. Okay. Now what you can do with that is you can use the combination of balance off, as I said earlier. Then you know for a given address, for a specific owner, how many tokens they own. And token of owner by index. There you can ask for a specific one when you're giving the address of the owner and the index. So the function you can see right here, the arguments are the address of the owner, as I said, and the index. And since you know how many of these indices you have to expect from the balance of function, it's essentially, let's say you have 10 of these tokens on one address, then the index 0 to 9 would be valid. So you could make these individual requests and say, okay, we have the address right here, and then we ask for index 0, then you get the token ID of the first one, then for 1, and so on, all the way up to 9. And that's a way to get all of these tokens of a specific owner. Similarly, the combination of total supply, so how many tokens, how many NFTs are there in total in that collection, and token by index, which is just an index for all of these tokens, makes all of the NFTs in the collection discoverable. So you could proceed the exact same way as I just explained, just for all tokens. So not just for an individual address or an individual owner, but for all tokens in the collection. Okay, and that's the idea of this enumerable or enumeration extension. The next extension we talk about is the metadata extension. It's almost always included. There are very few examples when this is not in there. And the idea is that you have simply a name for the token, the symbol, and the token URI. We will talk about that in a little bit when we look at how the information, how the unique characteristics of these tokens are actually stored, and why this makes a huge difference how it is stored. But it's even though it's an extension, it's not in the plain vanilla ERC721. I mean, it's almost always in there implemented. The metadata at the token URI is stored in JSON. What is important to understand is that it depends a lot on the front end, so on the marketplace, on the visualizer of these NFTs, which of these fields are actually supported. There are some some which are pretty much standard and are supported by all of these wallets, all of these marketplaces. But then there are also some more exotic ones which might be unique to some of these wallets and would not be shown in each and every one of them. But the idea is that there is a standardized way of how you show these properties, of how you represent these properties, I should say. For example, here in image, you have a URI pointing to the resource where the actual image file is stored, and then you have a description right here, you have the name right here, and then you have some attributes. In the attribute you have the trade type, the name of the trade, and the value, which is the value of the trade, so basically what it is. And you can also see that when we later on create our own NFT, which happens to be the mascot of this lecture, Hasoshi, then you will see that we also have implemented these traits and that they are part of the description also in JSON, of course, which is the standard way to do it. Now, one of the most important questions you always have to ask when you're dealing with NFTs is how are the information, how is the data stored? Where does it point to? Related to that concept, is there anyone who can change the data? It's great if in theory things are immutable, but then, for example, you would have an NFT where somebody would have special privileges to simply change the picture or change the traits, or you cannot even make sense of it. You simply don't know what the token represents without, let's say, a centralized entity. So it's important to be aware that this metadata is not necessarily secured by the blockchain. There's a large variety of ways of how you can store the information. And in practice, unfortunately, many people think these are technical details and they don't really care. They simply go to a wallet or let's say a marketplace, they see the pictures which show up there and they think it's an NFT, so it's mine, nobody can take that from me, it's immutable. But that's not always the case. These technical details, they matter a lot, and you have to be aware where the information is stored and what this actually means for the implementation. Now, the first thing, which is arguably the most secure and which is, I think, is a really good idea, is when the information itself is stored on the blockchain and can be replicated just by the information you find on the blockchain. The second option is that there is on the blockchain a verifiable hash, let's say of an image. The image itself is not on the blockchain, but you have a hash value, and then at least if you happen to have this image, then you know that's the one that the contract refers to. So it can still be looked at as immutable, but the information you need to make sense of that NFT, to know what it actually is not on the blockchain. In that case, it's rather just a cryptographic fingerprint in the form of the hash value. Then in some cases, it's off-chain stored, the metadata, on a decentralized file system such as IPFS. And I think the worst implementation, where you have to ask yourself why is this an NFT in the first place, is off-chain stored metadata on a centralized file system. So where essentially all the information is stored on a company's server. You cannot, without accessing, let's say, a proprietary website, you cannot even make sense of your NFT. You don't know what properties it has, and more importantly, this centralized operator can simply change the traits and everything about that NFT. Let's go with the first one. There's an example for an on-chain stored and replicable NFT. Let's go with Loot. As always, we have the smart contract linked reference right here, so you can look into that if you want to have some more information. But the idea is that the token URI function returns the base 64 encoded JSON file of the metadata. So basically, when you ask for the token URI, you get back the name, you get back the description, but you also get back the encoded SVG image. So it's an entire image on the blockchain, essentially, a vectorized image, which happens to be, in this case, just the attributes, because in this project, the entire idea is that it's this abstract way of describing, let's say, the gear of a character that can be used in any third-party protocol, in any third-party application, where you, for example, have things like a hot leather belt in this case, or a gold ring, which is just your gear. That's the entire thing. So it's basically this unique set of adventure gear you can collect, and it's represented in this case as an SVG. But it doesn't really matter what exactly it is in terms of the NFT itself. What I want to show you is how it is stored, and that's the unique thing. That's the idea that everything is on the blockchain. You don't need any additional information. You don't have any dependencies. Simply by the information on the blockchain, you can recreate that image and the properties, so you know exactly what the NFT is pointing to. Okay. The second thing, and there we also have an example with the CryptoPunks, is an off-chain picture. Which hashes to a specific hash value, and then you have to have this picture, of course. It's a little bit like a sprite map, where all of these individual, in this case 10,000 punks are on, and the entire sprite map is essentially hashed and secured on the blockchain. So even though you cannot replicate it just with the information on the blockchain, what you still can do, and that's extremely powerful, is you can verify that the information you get, or the information you store for your specific token or for the collection as a whole, is in fact correct, and nobody else can simply just change it because it's secured by a cryptographic hash value. And it can be either just one file, as I said, with sprites, or it can also be a Merkle tree, as is the case, for example, with hash masks, where you have a Merkle proof later on. So there are many different options, but the entire concept, the idea is that the image is secured on the blockchain, even though the image itself is not on the blockchain. Okay, that's the idea. Then you have the off-chain stored metadata on a decentralized file system. Here we have as an example the Bored Ape Yacht Club. Again, smart contract is linked. And the idea is that the token URI points to the metadata of the NFT, again stored in a JSON, but it's on IPFS, so on the Interplanetary File System, which is just a decentralized way to store information. And the entire JSON is on there, and then within the JSON, as you can see right here, there is another IPFS link to the image as an example, but there are also the traits in there. So you have the attributes, you have the trait type, let's say earring with the value silver hoop, you have the background, in this case it's orange, and so on. So it's stored on this decentralized file system, and you can request it via IPFS. And then last but not least, the off-chain stored metadata on a centralized file system. The example, probably the most prominent one, is CryptoKitties. Again, smart contract is here. And there the JSON file, including the image and pretty much everything, is just centralized. It's hosted by a centralized entity. In this case, it's Dapper Labs. So you have to access the website to even know which one of these cats you got and what properties they have. There is no other way for you to make sense when you look at the token, what it maps to, basically what kitty you got. You simply have to trust that centralized service, which also means if the centralized service is gone at some point, if they shut down the service, then it will be really, really hard. It will be impossible for you to find out which cat you actually have. So then it's at that point it's simply just a token with no reference whatsoever. And that's, as far as I'm concerned, not a good way of implementing these things. It's fine if it's just a game, but you have to be aware that you're losing many of the advantages of these NFTs if you have to rely on a centralized entity. This is just one of the examples. There are others, of course, but it's really important to be aware how this information is stored and what it does to your NFT. Now, if you're looking for a good example for the mutability of URIs, somebody has created these nice artworks right here as an NFT collection, and then at some point they simply used the mutability of the URI to change the image. and have added all of these rocks. So it's basically pictures of rocks to the tokens. And the rocks, of course, are a reference to rock pools in the DeFi space. So when you're cheating someone in DeFi, effectively when you're dumping all of your tokens as a creator, that's referred to as a rock pool. And they did that in this case just to demonstrate how important it is to look at how the information, how the image, the traits, the attributes are stored, and who can actually change that. Again, if external promises, let's say licenses are attached, then similarly to what happens with computer games where they cannot reissue them or remake them because they may have lost the license of an important franchise. With NFTs it can be even worse because then when they lose the license they might be forced to take down the images. And this happened in fact with an NFT collection called F1 Delta Time. We have referenced the article right here. Where they had to take down the pictures because they lost the license. And that's quite some contrast to when you, for example, think of physical trading cards where somebody prints them and they have the Formula One license at that point in time. Then, of course, they cannot be forced to change that later on because it's distributed with all of the owners and they cannot just recollect them or recall them and change everything. But with NFTs, depending on how it is implemented, depending on the options they have to change the URI and the image, this is perfectly feasible. And that's, again, just extremely important to be aware of these things and to look in the implementation, how the information of the NFT is stored and who might be able to change these things up. Now let me try to sum up everything we just said in that slide deck. And the first thing you have to be aware of is what NFTs are all about, because that's quite confusing. And when you go to Twitter, let's say, or to any online forum or website for that matter, you will stumble across threads where people say, you know, why would you ever buy an NFT? It doesn't really matter, because when you look at a CryptoPunk, no matter if you own it or not, you can always simply copy paste it, right? You can take a screenshot of that picture, or even easier, you can simply right click, copy, paste. And then there are all of these claims that they also own the NFT. But that's not what NFTs are about. The idea, as I mentioned earlier, is that you have these bragging rights and the option to transfer the digital original, quote unquote. So even though all of these pictures, all of these copies are exactly the same on the bit level, there is in the database only one original and there is only one owner to that original who can transfer it. So the right side of this table right here is usually, in most cases, controlled by the owner, and the owner can transfer that to someone else. Why do I say usually? Because there is one important exception you have to be aware of. In the last few months, there have been a lot of scam NFTs, so scam projects. And the way the scam works is they will transfer you a new NFT. So you will see that, for example, in your NFT wallet or on one of these marketplaces. And then they will place an offer on that NFT. And you think, okay, that's great. I just got airdropped an NFT and there is already an offer on it. And when you're trying to transfer it, it doesn't work. So it throws an error because the transfer function is adapted in a way that you're not in control of the transfer. The error you usually get is trying to lure you to a website, to a malicious one, where they are trying to conduct a phishing attack, get you to disclose your private key or mnemonic phrase, or scam you in any other way. Or the second thing they usually also do is try to get you to sign a message that can later on be used to basically approve themselves in one of your other NFTs. So there are various ways what they can do, and you have to be really, really careful when you get airdropped these NFTs. It's best simply not to interact with them to stay safe. And on the other side, the token ID, this may point to token-specific metadata, as I said. So it's basically the idea that it's not just a number, but also some images, some attributes, that basically represent that token and its unique characteristics. Otherwise, it would not be that exciting when you simply have just a token number and you don't know what to do with it and you don't know what it's referencing. So the entire attributes, the traits, the image is basically a reference through the token URI from the token ID on these specific things. Now there is also, I'm not sure if I should say a nice anecdote, but it's certainly something you should also be aware of because these things happen. And we have also linked the article. NFTs have made quite a splash in the art world. And when you went to Art Basel, for example, here in the city of Basel, or to any other art exhibition, there have been a lot of booths with NFTs and a lot of chatter about NFTs, and even dedicated exhibitions just for NFTs. And one of the larger art museums in Germany, actually, they got really lucky, and one of the people from that museum acquired 2 CryptoPunks really early on. And these CryptoPunks got extremely expensive over time. So when they realized that they had something really valuable in their possession, then this person tried to transfer these CryptoPunks to a new wallet. And the person simply went to Etherscan, copied the token contract address, not the destination address where you actually wanted to send these tokens, so these NFTs to, but the token contract address, and use this as the destination address for the transfer. And of course, these tokens are burned in that case, right? I mean, if that's not treated specifically and not checked, as is the case with some of these contracts, but unfortunately not with the CryptoPunks, then you can still see the CryptoPunks on the token contract. In fact, the CryptoPunk token contract is the new owner of these 2 CryptoPunks, but you cannot do anything about it. It's effectively burned. It's not accessible by anyone anymore. It's just on there. And this is, of course, a bummer. Now, the museum, they made some arguments that it doesn't really matter. They can still show them in the museum, but as a matter of fact, they are not in control of the CryptoPunks anymore. And that's certainly not a good thing, because they could also not sell them or transfer them to anyone else. So long story short, you have to be extremely careful when you're handling these NFTs. And that's exactly, as always, why we're recommending to only interact with our test nets, and by our examples are based on test networks. In this case, the Goerli test network. So the exercise we've prepared for you is that you can apply the learnings from this session and develop your own token contract, make use of the Open Zeppelin's ERC721 reference implementation, then deploy the contract on Goerli testnet, try minting and sending these tokens and grant some approvals. You can do that to your classmates or to anyone else when you're using 2 different EOAs, let's say, and then mint one of our Hasoshis on Goerli testnet. Recall, Hasoshi is the mascot of our lecture, the white rabbit. And of course, try to get the rare version. There are different variations of Hasoshi, as you will see. And it should be your goal to get the rarest one, of course.
Hello everyone, my name is Matthias Nadler. I'm a PhD candidate at the Uni Basel with a research focus on DeFi, and I'm part of the Open Lecture Core team. Today I'll walk you through these exercises, and we are going to create our own NFT from scratch. The NFT will be the Hasoshi, our Crypto Lectures mascot. Before we start coding, we need to prepare our assets, and for NFTs these will be images and metadata JSON files. We already prepared this, and you can see the images we're going to use for the NFTs here. There will be 10 different NFTs, and for these 10 NFTs we will have 4 different variants as well as 4 different background colors. For the variants we have the Sir Hasoshi, Captain Hasoshi and Super Hasoshi, as well as the Neo Hasoshi. And for the background colors we have green, mint, red and the elusive matrix background. we put all these images on our GitHub repository, and for each variant we also need to create a JSON file. The JSON file holds all the information, the metadata for each variant NFT, the name, the description, the link to the image, which, as I showed before, is stored on our GitHub repository. So this is a direct link to the raw image. If we paste this in the browser, you will see it links directly to the green Sir Hazoshi. Then we have the attributes, and the attributes define for each variant the relevant properties. In this case, we have the try type variant with the value Sir Hazoshi, and the tray type background with the value green. So this is the green Sir Hazoshi. A different example would be variant 6, which has the variant captain and the background red. Again, we store all these JSON files on our GitHub repository. You could store them anywhere else, even on-chain, but for our example, we go with GitHub. So let's get started with the code. First, as usual, create a new Solidity file. We'll call it Hazoshi. Don't forget the license identifier. We use the MIT license as usual. Then, of course, a disclaimer. For anything we do in this course, please don't use it with real funds. It is fine to deploy on a testnet. We use the same pragma as all our other files in the course, which is 0.8.9. And the contract name will also be Hazoshi. Now we will not be implementing NFT, the ERC721 from scratch. Instead, we will be using the OpenZeppelin standard implementation, the reference implementation. For this, I've prepared the GitHub repository from OpenZeppelin. If you decide to use a contract, select a release version. We use version 4.7.2. And navigate to the contracts folder under token and then ERC721. Here you can see the main contract as well as utilities and extensions. Let's take a look at the reference implementation now. You can see there are quite a lot of dependencies, and we will quickly go through them. So first, notice that the standard contract includes the metadata extension because it is almost always used, but it does not include the enumerable extension. So we will have to go look for that later. The dependencies include all the interfaces. The interfaces are to make sure we implement all the necessary functions as described in the lectures. Then we have a few libraries in the utils folder. These libraries enhance our address and integer data types. And finally, we have the ERC165. And this is to communicate and broadcast the interfaces that we use. You can see the ERC165 specs or the lecture slides for more details. The contract then inherits from ERC165 and implements the interfaces. We will not go through all of the code, but of note is the constructor. The ERC721 contract asks us to specify a name and a symbol for our NFT. And we will certainly do that once we implement it. Additionally, the supports interface function from ERC165 is overridden, and the new interfaces that we use, which are ERC721 and the ERC721 metadata, they are added to the supports interface function. The supercall simply calls the standard ERC165 function. So now that we have taken a look at the NFT base contract, let's also take a look at the enumerable extension. For this, we navigate to the extensions folder. and in the extensions folder open enumerable. This of course inherits from ERC721 itself, and that is also the only dependency. So everything we need is already in the base contract. We again also inherit from the interface to make sure that we implement all the necessary functions. Of note here is that there is no constructor in the enumerable extension, so when we inherit from this, we will have to use the constructor from the ERC721 base contract. To import this into Remix, simply copy the URL, the direct GitHub URL, and import it into Remix with the import statement. Simply paste the GitHub URL. And then we can inherit from this contract with the is keyword, and we inherit from the enumerable contract, which of course also includes the 721 base contract. With these simple steps, our Hasoshi contract already includes all the base functionality of an NFT. We just need to take care of the minting and the metadata now. So let's start with a token counter. Our contract needs to keep track which token IDs have been minted and what the next token ID to mint will be. We'll define this as a UINT token count. Next, we need the base URI. This is where our metadata will live. We'll come back to this in a bit. And since we have 10 variants, but no limit on how many Hasoshis can be minted, we need a mapping that stores for each token ID which variant was minted. Since both the token ID and the variant are UINTs, we define a UINT to UINT mapping, and we call it token variant. And this mapping will store for each token ID which Hasoshi variant it belongs to. Next, let's write the constructor. We don't need any specific constructor arguments, but we do need to call the constructor of the ERC721 base contract. Remember that the enumerable doesn't have a constructor, but the base contract does. And the two arguments are the name of the NFT and the symbol of the NFT, which we call Hasoshi and Has respectively. Now the base URI, this is where our metadata lives. And as we have seen before, we uploaded all the metadata to our GitHub repository for the open lectures. And the base URI is that part of the URL that is the same for each variant. And if we take a look at the URL first, let's view it in the raw format. If we take a look at the URL, the first part up to the 1.json is the base. This is the same for each variant. And then after this part, we have the token variant and then .json. So let's define the base URI as a link to the JSON folder on our GitHub. Next, we have to take care of the minting. So let's write the mint function. Again, we don't need any arguments. The function doesn't have to be payable. Minting will be free except for gas cost. We have 10 variants for our Hasoshis, and every time the mint function is called, we need to determine which of the 10 variants is minted. We would like this to be random, and more specifically, we would like a 1% chance to mint variant 10, and variant 10 will be the very elusive matrix Hasoshi, and an equal chance of 11% for all the other 9 variants. Now to achieve this, we need some form of randomness. And randomness on the blockchain, to achieve true randomness on the blockchain is very difficult. Usually you would go for a commit and reveal approach, but for our example we will use something more simple. We will simply use the block timestamp as a source of randomness. This is of course not recommended to be used in a production setting or on the mainnet. This way of generating randomness can be exploited very easily, but it will serve as an example for our test project here. So we need a random number from 1 to 100 or from 0 to 99. In other words, we need a 100-sided dice, a D100. And we define this D100 as block.timestamp with a modulo operator 100. This gives us the last 2 digits of the timestamp of the block where the mint transaction is mined. And we call this a random number from 0 to 99. Now, from this number, we can derive the variant. So we define the variant as a uint. And in the first step, we simply say the variant is equal to this D100 modulo 10 plus 1. Now, this means it is essentially equal to the last digit of the timestamp. We add 1, so the variant goes from 1 to 10 and not from 0 to 9. This is simply because we don't want the default value of 0 to resolve to a legitimate variant. The default value of 0 shouldn't resolve to a variant. That is why we want 1 to 10. Now, if we get the variant 10, we will need to do another check. And there's different ways to do this. One way is like this. We say if the variant is equal to 10, then instead of looking at the last digit of the timestamp, we look at the second to last digit. And one way to write it is variant equals a floor division of our D100 by 10 plus 1 again. So this will be the second to last digit of our timestamp. And if both the second to last and the last digit are a 9, then we will get the variant 10. In the other cases, we will get one of the other 9 variants with a probability of 11%. Now that we know which variant to mint, we need to know which token ID to mint. And to do this, we will look at the token count variable, and we will first increment it by 1 and then assign it to the token ID variable for the current token to mint. The way to write this in Solidity is token ID equals ++ token count. The ++ simply means increment this variable by 1 before assigning it to the left-hand side. So we start with token count equal to 0 with a fresh contract, and the first minted token will have the token ID 1 because it is first incremented from 0 to 1 and then assigned to the token ID. Again, this is important because we don't want token ID 0 to be an actional token, because 0 is the default value and the default value shouldn't resolve to a valid token. Next, we assign the variant to the token ID in our mapping. So the token that we will mint has the variant that we just determined. And finally, we have to actually mint the token. And for this, let's switch over to the Open Zeppelin contract again. And let's go to the base contract where the minting is handled. Scroll down and find the mint function. There is a save mint and a mint function. We will use the save mint function. And the parameters are the address that you would like to mint the token to and the token ID that you want to mint. The function is internal, so we can call this from our function, but it cannot be called externally. So when implementing ERC721 from Open Zeppelin, you always have to write your own mint function. And the save mint function will check on ERC721 received before minting the token. So let's call this function from here. And as the to address, we will use the message sender. So the person that, or the address that called the mint function, and the token ID, we will use the token ID that we derived 2 lines above. That's it for the mint function. Next, we have to take care of the metadata and link it to our NFTs. So the way this is done in ERC721 is with the token URI function, which returns a URI where the metadata of a specific token is stored. Let's first take a look at how OpenZeppelin does this. We will search for the token URI function. And we can see here the token URI function takes a token ID, and it is a public function. So even if we wouldn't do anything at all, this function would exist because it's part of the specification. It can be called and it would return something, but it would definitely not return what we wanted to return. So we need to override this function and make sure it returns an exact path to our metadata. And also note that there's a require minted statement in here. We should make sure to also include this so we get a revert if the token doesn't exist. To make it easier for us, we copy over the function signature. Function signature has to be exactly the same. And we don't plan on overriding this in the future, so we can delete the virtual keyword. But everything else stays the same. We want to return a string that points to the metadata of a specific token. Now remember, the metadata for our tokens is stored in our GitHub repository. And the first part of the link to this metadata is stored in the base URI variable. And what we need after this is the token variant and then a .json. So we need 3 things: the base URI, which we have, the token variant, and a .json, which is a simple string. To get the token variant, we can use our mapping, and we will get the token variant in the mapping with the token ID that the function was called. And then we can return the full URI string. We do this by concatenating these 3 variables. So return a string. Concatenating works with the function abi.encode packed. And this function takes any number of strings that are concatenated. So first, the base URI, second, the token variant, and third, the .json. Now, this will not work because variant is not a string, it is a UINT. And to make this work, we first need to convert it to a string. Let's actually see how OpenZeppelin solved this issue. So let's again switch over to the OpenZeppelin code. And we can see they are doing something fairly similar to what we are doing. String, ABI encode packed, base URI, and then they use this token ID .toString. So in our case, this would be variant toString. So let's try this. But the compiler will give us an error. It says toString is not found or not visible for the type UINT256. And the reason for this is because integers don't have a toString function. So OpenZeppelin solves this by importing a strings library for UINT256. This strings library adds a number of useful functions to the integer variable types. It's imported from the global utility directory. And since we inherit from this contract, we will also have this library already imported in our contract, which means we can simply add the statement on top using strings for uint 256. And this will give us access to the toString function. So now the contract compiles, no more errors, and that is actually already it. We are done. The NFT is finished. Next, we will look at deploying the NFT and interacting with the deployed version. So let's switch over to the deployment tab. And we are using the Girly network. Make sure your MetaMask is connected, and here you can see a list of all the contracts that we imported. So make sure the correct one is selected, the Hazoshi contract. We don't have any constructor variables, and then let's deploy it. Let's check our transaction on Etherscan. Note this is the Girly Etherscan website, and let's wait for the confirmation. And it's confirmed. So as you can see from the receipt, a new contract was deployed. Let's take a look. Etherscan, after the contract is processed, will recognize this as an ERC721 contract. So let's check back in a bit. And first, let's go back to Remix and let's see if we can interact with the contract. Check maybe the name, which should be Hazoshi. And the symbol has, so this works. And as you can see, all the standard NFT functions are correctly implemented by using the OpenZeppelin standard. Let's try minting Hazoshi. This will trigger a transaction, which we can confirm. No Ether needs to be sent. Let's check our transaction on Etherscan and again wait for a confirmation. And it's confirmed. And as you can already see, Etherscan has recognized our contract as an ERC721 token contract, and it tells us the token ID 1 has been sent from the 0 address to us. So this is standard for minting a token. It is sent from the 0 address to the person that minted it. This is the overview of the Hazoshi token as it is viewed on Etherscan. So let's go back to Remix once more. Check if the total supply is updated. Yes, indeed. And we can try a few of the other functions. The balance for our address is now 1 token. And these are the enumerable functions which we could try. But let's actually check if the token URI is received properly. So we check the token URI for token 1, and this links to our GitHub repository as we planned. Token variant is number 5. And if we try to query the token URI for token 2, this will give us an error, invalid token ID. And note, we never implemented this error. This error is specified in the OpenZeppelin reference implementation. So we really don't need to specify anything further. We just use the template for ERC721. Let's mint a few more. With the power of video editing, I'm going to speed this process up until we have a few more Hazoshis minted. And here we are. 3 more tokens have been minted, so we are at token ID 4. Let's check the token tracker on Etherscan, and we can see the total supply has been updated. 4 tokens have been minted, 1 holder. This looks correct. And to double check in Remix, total supply is now 4. We can now query the token URI for token 2. And let's also check the balance, yes. And let's check the enumerable functionalities. So let's check the token ID 1 for my account, which is the token 2. Token ID 0 is the token 1. And the global token by index, global index 0 will also be token 1. And if we try to go out of bounds, we will get an error, a reverted transaction. Again, this is implemented by the ERC721 enumerable by OpenZeppelin. So let's actually look at our NFTs. For this, we can use any NFT browser that supports the Girly testnet. We choose OpenSea, go to testnets.opensea.io. You can also do this for yourself. And then we have to copy our contract address and enter it in the search field. And OpenSea has already indexed our collection. So we can see here the Hazoshi collection has been found. And we can for the first time actually see what we minted exactly. The collection consists of 4 NFTs that we minted. We actually minted the Captain Hazoshi twice, with a mint background. So let's take a closer look at the token ID 1, which is a red Super Hazoshi. So as you can see, the attributes that we defined in the JSON file are now beautifully displayed on OpenSea. The description, the most heroic of Hazoshis, which is of course the Super Hazoshi, with the traits for variant and background. OpenSea also displays quite a few additional information. There is a sell button if you want to sell the NFT, and a transaction history on the bottom where we can see it was minted from the 0 address to ourselves. And we can take a look at a different NFT and we can see the properties and descriptions for all of them. So yes, this concludes the NFT exercise. Please feel free to replicate this, maybe design your own NFT and deploy it on a testnet. Have fun. So for the second part of the exercise, we will go over how you can mint a Hazoshi, or as many as you want, and how to transfer these NFTs and also how to view them on OpenSea. So first thing you have to do is go to this link. This is on Girly Etherscan, the Hazoshi token contract. The link will be in the description at Teachable and also in the description of this video. So make sure you're on the token tracker for Hazoshi and then go to the contracts tab. Here you can see the source code because we have verified the contract. You can see the part that we wrote, full NFT in 45 lines. And you can also see the dependencies that we imported from OpenZeppelin. Now, Etherscan for verified contracts offers a full interface for all the read and write functions. So very similar to Remix, we can go through this and check the total supply, maybe check the name, symbol, etc. Is this how you are used to from Remix? Also, functions that require an argument can be called. We can copy the address here and maybe check the balance of the address. And now we switch over to the right tab where we have all the functions that are not view or pure. And the one we are obviously interested in is the mint function. There's no arguments to it. We can simply mint our token. But first, we have to connect our MetaMask to Etherscan. You can do this by clicking the Connect to Web3 button. Please read the warning. This is still a feature in beta. And be careful, especially when you use it with real funds. So connecting to MetaMask means the website can send information to your MetaMask. You can view your currently connected sites in MetaMask by clicking here and then connected sites. This will list all the sites where you have linked your wallets to. Note that this will not put your funds at risk. All this does is allow the site to send certain data to MetaMask, for example, to display and let you sign a transaction. And this is what we are going to do here. Once you're connected, we can click the right button in the mint function. And this will prompt MetaMask to show us a transaction that we'd like to execute. We can inspect the transaction before we sign it. Can check the data that is sent along with the transaction, which for the mint function will be no data. This is similar to Remix. And once we have inspected the transaction, we confirm and send the transaction. You can either click on the View Your Transaction button or, as usual in MetaMask, view the transaction on Block Explorer. So let's wait for a confirmation. And it's confirmed. The transaction looks very similar to what we have seen in the last exercise. You can see ERC721 token transaction. Token number 5 has been minted to your address. Now, in the Asset tab in MetaMask, you will not see this token by default, but you can manually import it. To do this, you have to copy the contract address for the token you'd like to import. Then click on Import Tokens and paste the address. MetaMask will automatically know the token symbol, and the decimals for NFTs are always 0. So my address now has 5 tokens. You can import this and then it will show up in MetaMask under your Asset tab. However, sending NFTs directly with the MetaMask application is not yet supported. So we will have to do this manually. And for this, we will again go to the right contract tab. And here we can see 3 different transfer functions: safe transfer from with data, and also the normal transfer from. We will be using the basic safe transfer from function. And the from address, we have to use our address where the tokens are located. So copy this. The to address, we will use our second account in our wallet. So switch over and copy this. And the token ID will be the one we just minted, which is token ID 5. Now make sure you switch back to the account that holds the token, otherwise you cannot transfer your tokens if you try to sign this from a different account. Click the right button, and here you can see again the transaction that MetaMask wants us to confirm. And this is pretty cool. MetaMask will show you a small preview of the token you are trying to send. It is a Hazoshi and it has a mint background. And if I see this correctly, it is a Captain Hazoshi. So inspect the transaction, make sure this is the NFT you want to send, make sure the recipient address is correct, and then click confirm. View the transaction, And for one last time, we will wait for a confirmation. And it's confirmed. So here you can see an ERC721 token transfer from our first account to our second account, and Etherscan will very nicely display this in a readable format. If we go back to the read contract and check the balance of our second account, for this we have to copy the address of our second account, and this should be 1 now, which it is. So the token has been transferred, and we can also check the token ID that we received, which is the index 0, which is token ID 5 as expected. Now for the last part, let's go back to testnets.opensea.io and copy the contract address to find the collection. In the collection, we will see all the NFTs, all the Hazoshis that have been minted. You can also connect your wallet to OpenSea. You can do this by clicking on Profile, connect with MetaMask as usual, and switch to the correct account. Account 2 in this case. And if you connect for the first time, you have to accept and sign the terms of service, which is fully done in Web3. And once you have done this, you will see all your NFTs on the testnets. And this is the Captain Hazoshi that we received. Token ID 5 was first minted and then transferred. That's it. Congratulations on your Hazoshi. And now back to Professor Schär.
All right, thank you very much, Matthias. Great job with the exercises, and thanks to all of you as well for watching the video. We hope that you've learned about NFTs, their applications, of course about the ERC721 token standard, and also about potential risks and pitfalls in the context of NFTs. But most importantly, we hope that you got to mint the rarest of all Hazoshis. So with that, stay curious. See you soon.